verify what we have been doing up to now. We were examining the sequential circuits. While we are examining these sequential circuits, we mentioned the sequential circuit in general as a circuit. And then we said in this circuit we've got memory elements in it. So you could see these memory elements here. And then we said these memory elements fundamental memory elements. That means all the other memory elements can be produced by using these fundamental memory elements. We introduced these memory elements to you already. So that was NOR-type memory elements and NAND-type memory elements. Now in this frame, which is this frame, we will be examining a problem, and we're going to find a solution to that problem as well. What is the problem? Problem is this. Although we said that some of the inputs for NOR case and NAND case, which are 1, 1 and 0, 0 forbidden inputs exist, you can say that I'm not going to apply these inputs, but still unwanted application is possible. That's the problem. So I will explain this problem first to you. Let me go in details and explain it to you. So escape from here. Leave it out and open this and come to this. Open board. Okay, here you are. So you see here how the problem arises. So just remind you, this memory element, SR memory element, definition relation is this. A bit fast. Input 0, 0, 0, 1, 1, 1, 1, 0. And small y, that's the present state 0 and 1. Inside we've got the capital Y, that's the next state. So we said the input is 0, 0, no change. When it is 0, 1, whatever S says is going to be seen at the output 0, 0. That's forbidden. And when these are different, S and R values different, independent from the present state, your output is 1, 1. So that is forbidden. So all the others are allowed. Assume that you have this SR memory element and you are applying 1, 0 and then 0, 1. This 2 is acceptable, isn't it? 1, 0 is this input, it's not forbidden, and this input also is not forbidden, that's 0, 1. But when we apply these two inputs, one after the other, so that is the example here, you cannot, so S value is going to change from 1 to 0, and R value is going to change from 0 to 1. So you cannot change those two inputs at the same time. That's something impossible. So what happens is this. If S changes, let me show you the time when S changes here in red. So this is S change. And another color, this is the R change. Since we couldn't change those two inputs at the same time, there is a time difference here. Let's say delta t. So what happened is this. I can tell you this R value has changed earlier than the S value. In between, you're going to observe 1, 1. So what happened is this. In between, this forbidden input has been applied, although we didn't want to do that. We didn't want to do. All we want to do is to apply 1, 0 after the 0, 0 apply 0, 1 after 1, 0. So these are allowed, but meantime, although I didn't want it, 1, 1 input has been applied to my SR memory element. So that is the problem. So how we are going to solve this problem is introduce a new input. So in Turkish it is saat, so that's called sometimes clock, and sometimes we are going to call it, in this case, we are going to use it enable input. What does this enable input do is this. When this forbidden input, when let's say another way around, when the allowed inputs applied, there is going to be a pulse 1 available, and our SR memory element enable is going to work for these 1, 1 values. When enable input is 1, this is going to work. When it is 0, it's not going to work. So what happens is this. If I apply this 1, 1, while S value, R value is 1, 0 and 0, 1, but do not work at that delta time interval since the enable input is 0. So this is not going to work. So that is the solution. What happens is this. Since it is not going to work, that means the application of 1, 1 is not effective. Therefore, that is going to be a solution. So what is the cost of this solution? So we can explain it to you in here. Here you are. You see the original SR memory element was did have only 2 gates. Now we've got 4 gates, and in addition to that, we've got an enable input, and in addition to that, when we've got 2 gates only, we've got another 2 gates here, so delay is doubled as well. So in order to solve the problem, solution cost is doubled delay time, doubled gate costs, and additional input enabled. So that is what we're going to pay. When we pay that, whether it works properly or not, let's examine it now. So you see this SR and S star R star, that's the definition relation of this. Now I'm going to examine now this SR memory element. So I'm going to show you that this SR memory element is going to behave as it is definition relation. On the other hand, when the forbidden input is applied, it is not going to work. So let's see it now. So when enable is 0, let me examine this now first. Enable is 0. Enable is 0, that means this input is 0. Whatever the other input is, multiplication gives you 0. Prime of it, because of this NAND, is going to be 1. So in this case, it's going to be 1 as well. So when S star and R star values are 1, 1, which is this case, what I am going to observe at the output is 0, 1. That means no change. So for this input, no change. So that means not working. Okay. So when I have got the forbidden input comes to this gates, then it's not going to work because I'm going to make this enable input 0. So when enable input is 1, this should be working. That means in this case, in terms of these input SR, this definition relation is going to be valid. Let's show this now. So that now I'm going to clear this enable 0 input and make it 1. Enable 1. Enable 1 means that is 1 and that is 1. So the output of this NAND gate is going to be S prime. 1 time S gives you S prime of it, S prime, and R prime here. So in this case, let me examine whether the behavior of this SR memory element, which is inside that box, working properly. That means according to this definition relation. Let's check it. When SR values are 0, 0, so I'm going to examine, let's make it red now. SR input 0, 0, what happens? That's going to be 0, and that's going to be 0, and that's going to be prime of it is 1, and that's going to be 1. When S star and R star is 1, 1, my output is 0, 1. This output is also the output of that red box. That means SR memory elements. That means this, isn't it? So that means I have shown you now this column in this definition relation is true for these S0 and R0 inputs. So let's examine this one now and change the color to blue. So when I apply 0, 1 here, 0, 1 here, that is going to be prime of it, that's going to be 1. And that's going to be prime of it 0. When it is 1, 0, S star R star value is 1, 0, that's that case, isn't it? And my output is going to be 0, 0. Now, input 0, 1 means this. In this case, S star R star output is the same as my SR memory element output as well, so that is the same as this. So I validate, that is the validation of this column here in the definition relation. And change the color to green now and apply now 1, 0. When you apply 1, 0, that's going to be 0, prime of it, 0, and that's going to be 1, prime of this. So when you apply 0, 1, that means that column. So if you consider this box here, SR, this is 1, 0, that is that 1. If you consider S star R star, it's going to be this, and the output is 1, 1. So in the definition relation is 1, 1 as well. So that has been validated now for this input. So for the 1, 1 input, I said is never to come here, isn't it? Why is that? Because this is prime and that's prime, isn't it? Let's say if you apply 1, 1 here, S equal to 1, R equal to 1, I'm going to make that enable equal to 0. When I make this enable equal to 0, this memory element is not going to work. So I solved the problem. So I have done it for this SR memory element. So here you are, D flip-flop by using S star R star fundamental memory element is introduced like that. So you can check that definition of this box, here. Behavior of this box is the same as the definition relation of D flip-flop. So you can analyze this, how you're going to do it. Let me do it now. So when D equal to 0, so that means 0, whatever this is going to be. So I'm considering both of them as in there. Now I'm not going to give you all the details, but just give you the hint. So this is enable input. When enable input is equal to 0, so that means that's 0, 0, that's going to be 1, 1, isn't it? 0 times whatever this input is, multiplication gives you 0. Because of this NAND, it's going to be 1 here. Similarly, that's going to be 1 as well. When it is 1, 1, so I'll draw you the definition relation S star and R star. Not shown here, but I can easily write it here. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. When it is 0, 0, not applied. When it is 0, 1, what R star says, 1, 1. When it is 1, 1, no change, and 0, 0 here. That's the definition relation. Now, when you got 1, 1 here, the definition relation tells me of this element definition relation, tells me no change. That means not working. What is not working? That circuit here is not working when enable is 0. When enable is equal to 1, so I am leaving it to you to examine the behavior of this box D-type memory element is the same as the definition relation of this memory element. I have done the similar thing for the SR flip-flop here. So I am leaving the other one to you to prove. That means check the D flip-flop behavior is the same as the definition relation of this D memory element. That means behavior of that circuit. So similarly, the solution of the problem is double the delay time, add 2 additional gates, and 1 additional input enable. So that is the end of this video then.